In 5C we're going to be looking in particular at combined arithmetic and geometric sequences which you've met before. Sequences where you do a multiply and an addition or a subtraction, and we'll look at them both with formulas and with recurrence relations. Just as a summary so far, what an arithmetic sequence: A is the first term, D is the common difference. There's a rule there and there's a recurrence relation there for you to read. Pause if you need to read it to yourselves or copy it down. And the geometric sequence: A is the first term and R is the common ratio. That's what you've done so far. Now we're going to be combining those two together, seeing what happens. Now here's an example. We have a trout farm. Currently there are 10,000 trout in the pond. Probably not as big as the one in the picture. Now, breeding that's what they're there for. The population is increasing by breeding by 10%, but after a month, 3,000 of them are then caught and sold, and that's why the farm is there. So, how many trout will be in the pond? Well, after 1 month, that's straightforward, I think. Let's see how you do that. One way to do it is to put into your graphics calculator. Now, underneath that black blob, it should be 1, because it's 1.1. As you know, increasing by 10% is multiplying by 1.1 times the previous term minus 3,000, and the first term is 10,000. That's how many we start with. If you have put that in correctly and then press second function table, you will see the numbers. So after 1 month, starting with 10,000, there will be 8,000, and then 5,800, and then 3,380, 718, and if the farmer keeps going like that, then he won't have any trout left. He's taking too many out. So there's a practical application. A farmer would need to know how many fish to catch to sell without depleting his stock and ruining his business. It's obviously going to have to be a lot less. If you want to see what the graph of that looks like, just make sure that the window is showing the right figures. So I'm just showing the first 10 values of n, 1 to 10, and in fact, because my x-axis is only going 1 to 6, then I only want to see the x values 1 to 6, and y-max starting at 10,000 going down to 0. Let's see what that looks like. So there you go. Probably could have been a bit better, that graph, but you get the general idea, showing the positive values only. Anyway, that's an example of a combined arithmetic and a geometric sequence. The arithmetic part is the minus 3,000, and the geometric part is multiplying by 1.1. The letters to use for a combination of growth and decay: we're still going to have Vn for the nth term, V0 for the starting value of the sequence. Little r is the percentage change in each time period, and d is the difference or the amount of the arithmetic change, and your formula is then going to look like that. Now, where does that capital R come from? Well, you've seen it before. Capital R is 1 plus little r over 100 for growth, and r minus little r over 100 for decay. So nothing new there really, it's just a combination of the two rules. See if you're going to put that into a full practice. Each day 1.4% of the water in a swimming pool is lost due to evaporation, and 1,000 litres are added, starting with 150,000 litres. So we're going to run the sequences W, N. Now the recurrence relation that models the amount of water in the pool. W0 equals 150,000. Wn plus 1 equals R times Wn plus 1,000. The question is, what is capital R? Well, it's 1.4%. We're losing 1.4%. 1.4 is 0.014, so 1 minus 0.014 is 0.986. D is 1,000, W0 is 150,000. If you put those numbers into the calculator, you'll get 0.986 times U brackets n minus 1, close brackets, plus 1000. Starting value is 150,000. And then second function table will tell you the values after however many days that you want. On my particular display I've got n equals 1, which is 150,000, so in fact after 1 year will be the second value, so don't get confused about that. Maybe we should start with n equals 0 on that display, which you can do by going to table set. This is taken out of the exercise at the end of the chapter. You're asked to look at a recurrence relation and identify whether it's arithmetic, geometric or combined, and its direction. Is it growing or decaying? Do a couple of them for you so you get the idea. In A, we're only multiplying, so that's going to be geometric, and the numbers are going to get bigger every time, so that's going to be an example of growth. It'll be decay if the multiplier was less than 1. B is arithmetic. The numbers are going up by 7, so that's an example of growth, arithmetic growth. The third one is multiply and then subtract, so that's a combination. And it looks like the numbers are going to be growing because multiplying by 3 and only subtracting 5 is never going to produce a sequence that are getting smaller. I'll leave you to do the other 3. Pause while you think about it and then check your answers in the back. Here's another question out of the exercise book. Now, at this time we're given a recurrence relation and we're asked to identify the various bits of information from it. How many mice were initially in the population? That's your 8,600. The annual percentage rate of increase in the mice. Now, you've got to unpack 1.15. That is increasing by 0.15, and 0.15 is 15%. So the answer to that one is 15%. How many mice leave the population each year is 750. Now, overall, is the population of mice growing or decaying? What it looks like is growing, but really you need to stick the numbers into the calculator to see what comes out and double check on that. So I've done that there. 1.15 it should say, and then minus 750 starting with 8,600. Those numbers are definitely getting bigger, so it's definitely growth. And again I've got n starting at 1, but that's actually the 0. So after 5 years we want number 6, which is 12241. If you want to graph it, I put in 50 values this time, and I've allowed for up to 100,000 mice. God forbid, obviously no cats around, and that's what the graph would look like if they're allowed to grow unchecked. Alright, that's 5C. Have a look at questions 1 to 3, which use the formula, and questions 4 to 9, which use recurrence relations.